Okay, hello everyone. Today we will move on to hypothesis testing part 5, which will cover last part of the hypothesis testing, Neyman-Pearson lemma and likelihood ratio tests. Okay. The chapter 10.10 is about power of test and the Neyman-Pearson lemma. And we learned about lots of test statistics. And one of the problem is that is it good test statistic? Probably we can construct other test statistics as well. So let's assume that we are testing h0 is mu equals mu 0 and the alternative hypothesis is mu is greater than mu 0, then we can pick any distribution under the null hypothesis. We can pick any test statistic like yeah, user test statistic would be y bar, and whether a y bar is large enough than mu 0. We use this as our test statistic. However, probably we can also use y1, or we can use y1 plus y2 divided by 2. We can also use these type of estimators as test statistic. But why we choose y bar? And we want to think about what is a good test statistic. So under the null hypothesis, mu equals mu 0, and what we want is probably we want to have smaller variance of our test statistic, because if real mu is greater than mu 0, then we probably observe our test statistic is large enough. If y bar is larger than k, probably that would be the evidence of the alternative hypothesis is true. To do that, we want to have less variance, and then probably we will have more probability. So the rejection region would be larger and larger. And if the alternative is true, we want to reject the null hypothesis. In that case, probably we would have larger rejection regions. And also for the test statistic side, probably we want to have the estimator with smaller variance, and that's the concept of power. Something we want to talk here. So the goodness of a test is measured by alpha and beta, the probability of type 1 and type 2 errors. And usually we fix the type 1 error. So usually the type 1 error is alpha, which is the probability of rejecting H0. Alpha is probability of rejecting H0 under H0 is true. So the probability of alpha is this area, and let's say if alpha is 0.05, this is 0.05, and the beta, the type 2 error, is that beta is probability of accepting H0. Accept H0 given H1 is true. So the alternative is true. So true mu would be somewhere here. Then maybe the distribution, true distribution, would be this one. Then what would be the error? What would be the probability of accepting H0, which is the probability in here. So we can calculate the area of this side to calculate the beta. And so now let's ask what is a good test statistic. Then what we want is that we want to have less type 1 error and also less type 2 error. So we want to minimize If we fix the type 1 error rate alpha, if we fix this error rate, then what we want is we want to minimize beta, or we want to maximize 1 minus beta, which is power. We will here the name of the chapter 10.10 is power of test and the Neyman-Pearson lemma, and the definition of power is 1 minus beta, and so power is this part. We want to maximize this part, and we want to have a test statistic that maximize power. That's the concept in here. So let's move on to definition 10.3. Suppose that W is the test statistic and rejection region is the RR is the rejection region for a test of a hypothesis involving the value of a parameter theta. Okay, then the power of the test denoted by power theta is the probability that the test will lead to rejection of H null when the actual parameter value is theta. That is like this. So let's think about this situation from the previous example. So here we have. So let's say this is mu 0, and let's say this is theta 0, and this is true parameter theta, and then and let's assume that the H null is mu, theta is theta 0, and let's say our alternative hypothesis is theta is greater than theta 0, and let's say true parameter is theta, and under the null, the distribution is like this, and the rejection region would be this area. Let's say our alpha is 0.05, then the rejection region is this area. So this is determined, and if the true parameter theta is here, then the true distribution would be this one, and then the power is W in rejection region when the parameter value is theta. So the power of theta is area here. So the power is function of theta. If theta is theta 0, if theta is theta, if power theta, if theta is theta 0, then the true distribution would be this one. Then the area of this one, this is alpha. So let's check the figure 10.13. A typical power curve for the test of this thing. We fix the level alpha, so the area here is actually alpha. So if theta is exactly theta 0, then the probability is alpha. And let's move our theta a bit more. So let's move our theta to here. If true theta is here, then the true distribution would be this one. Then we will have the power would be this area. So it would be a bit bigger. And as we move our theta to this side, the power goes higher and higher. The area of this and the area of that, and also if we move theta even farther, then the area would be close to 1. So this is a typical power curve for a given test, and the ideal power would be like this. If theta is theta 0, then we the power of theta is 0. But in other case, if theta is not equal to theta 0, then we want to detect that is power, which is 1. So this would be ideal case. However, what we observe in user case, what we observe is this situation, figure 10.13. And so this is definition of power, and power is a function of two parameter theta, and that's what and actually this power is 1 minus beta, the type 2 error rate. Let's talk this in next slide. Okay, let's learn about relationship between power and beta. Let's think about this situation. We are testing H null is theta 0, and H alternative is theta is not equal to theta 0. In this case, under the null situation, let's say our test statistic follow a normal distribution, something like this, and here's theta 0. Then let's see. We can decide the rejection region with alpha. This is alpha over 2. The area here is also alpha over 2. So this is underlying null distribution of the test statistic. And let's say theta A is the value of theta in the alternative hypothesis. And so power theta A, if the true theta is theta A, then let's say this is theta A. If the truth is theta is theta A, then the distribution would be like this. And then the power should be the area here. And actually area here is 1 minus this green area, and actually this green area is beta. So the green area is the probability of rejecting accepting H0, accept H0 under H1 is true. So the green area is beta, the beta type 2 error rate, and so we can represent the power of a test as 1 minus beta. So this is the relationship between power and beta. Let's try to solve exercise problem 10.89. Refer to exercise 10.5. Find the power of a test 1 for each alternative in A to E. Here is exercise 10.5, and we want to consider the test 1. So let y1 and y2 be independent and identically distributed with a uniform distribution over interval here. And for testing, H0 is 0 versus alternative is theta is greater than 0. We have two competing tests, and test 1 is reject H0 if y1 is greater than 0.95. Okay, so the test statistic is here is y1. And what would be the distribution of y1? So y1 is uniformly distributed from interval theta to theta plus 1. And under the null, if theta is 0, if theta is 0, then under the null, the distribution of y1 is uniform distribution. So here is 1. And so the rejection region is y1 is greater than 0.95. So here is 0.95, and so rejection region is here. Or rejection region is here. Okay, and what is alpha? What is alpha? Alpha is the probability of rejecting null under H0 is true. So the area of here is alpha, and this is 0.05. So this test is alpha equals 0.05 test. And let's move on to 10.89 again. Refer to exercise 10.5. Find the power of test 1 for each alternative in A to E. So let's say we want to calculate power of theta equals 0.1. We want to calculate power of 0.1, which is the probability of rejecting null, reject H0 under theta, true theta is 0.1. Okay, so if true theta is 0.1, what would be the graph? If true theta is 0.1, then the true distribution would be something like here. So the 1.1. So the rejecting H0, the probability would be area here, and that would be 0.1 plus 0.05. So this would be 0.1 plus 0.05, and so this is 0.15. And similarly, we can calculate power 0.4, and this is 0.4 plus 0.05, which is 0.45, and for power 0.7, this is 0.75, and for power 1, this is 1. Okay, because when power theta is 1, the situation is so from 0 to 1, 1. So the distribution of y1 is this thing, and the rejection region is this area, and the total area of this region is 1. So this is 1. And sketch a graph of the power function. So number E is sketch the graph of the power function, and when theta is 0, the probability is 0.05. So when theta is 0, here is 0.05, and when does it get to 1? That is actually power 0.95 is 1. Power is 1 at here, so here is 0.95, and at 0.95 it reaches to 1, and actually the relationship is linear. The area here is linearly increasing, so the shape is like this. So this is so this part is theta, and y-axis is power of theta. Okay, so this is power function graph. Definition 10.4 talks about a concept of simple hypothesis. If a random sample is taken from a distribution with parameter theta, a hypothesis is said to be a simple hypothesis if that hypothesis is uniquely specifies the distribution of the population from which the sample is taken. Any hypothesis that is not a simple hypothesis is called composite hypothesis. Let me give you a simple example to understand what is simple hypothesis and what is composite hypothesis. Let y1 to yn it follows normal distribution with mu and sigma square equals 1. And if the null hypothesis is mu equals 5, then if we plug in mu equals 5 here, then the sample will follow the normal distribution with 5 and 1. So with the hypothesis, the distribution is uniquely specified like this. So this is simple hypothesis. And what about composite hypothesis? Let y1 to yn follows normal distribution with mean mu and sigma square. And if our hypothesis is mu equals 5, then if we plug in mu equals 5 here, again, we still have the unknown parameter sigma square, and we cannot specify the distribution of the sample is not uniquely specified. So in this case, we say this is composite hypothesis. Okay, let's move on to theorem 10.1, the Neyman-Pearson lemma. Suppose that we wish to test the simple null hypothesis H0, which is theta is equal to theta 0, versus the simple alternative hypothesis HA is equal to theta A, based on a random sample of y1 to yn from a distribution with parameter theta. Let's L theta denote the likelihood of the sample when the value of parameter is theta. And then for a given alpha, the test that maximizes the power at theta A has a rejection region determined by this way. This one would make sense because if the alternative hypothesis is true, then probably we will have a larger value of L theta alpha. So this L theta is the likelihood of the data likelihood. If the truth is theta A, then L theta A would be larger. Then if L theta A is larger, then this value would be smaller. So if this one is small enough, then it would be the evidence of rejecting the null situation. So for the likelihood perspective, if likelihood of theta 0 divided by likelihood of theta A, if this value is small enough, we will reject the null hypothesis. So this would be so this rejection region would make sense, and the more important result is that if we decide our rejection region this way, then for a given alpha, the test that maximizes the power at theta A has a rejection region of this. So what it implies is that this one maximize the power at theta A. So this is the important result. If we decide our rejection region this way, then this will maximize the power of theta A. Okay, and the value of k is chosen so that the test has the desirable value for alpha. So if we find the distribution related to this test statistic, then we can calculate the value k with the distribution of that using the underlying null distribution. We can calculate k, and such a test is a most powerful alpha level test for H0 versus HA. So this is very fascinating result. If we derive our test using this way, then it will imply that our test is the most powerful test. The most powerful test implies that it will have largest rejection region. So when we are doing hypothesis test, most of times we want to reject the null hypothesis, and we want to so this is new knowledge, and we want to share the new knowledge, and then to do that we want to reject the null hypothesis, and we want to rooting for the null alternative hypothesis, and then and so we want to reject the null hypothesis, and we want to have more power. So if the underlying distribution So theta equals theta 0. If this is the null distribution, and we want to have the largest rejection region to reject the null situation, and and so if we take our rejection region this way, then this one implies that it maximizes the power. So if the alternative distribution is something like this, then power is this thing, and um, and if given the condition, given the situation, if we take our test statistic this way, then it will give us the maximized power, and so this one is good thing to use. So most of times you want to reject the null hypothesis, and if you pick if we pick our test statistic this way, then it will imply that this one have the maximized power, and so that's we have good reason to use this one. Okay. For the proof of the theorem 10.1, actually the exact proof of this one is the out of the scope of this course. So we will learn how we apply this lemma. Okay. Let's move on to example 10.22. Suppose that y represents a single observation from a population with probability this one, and find the most powerful test with significance level alpha equals 0.05 to test this thing. To find the most powerful test, we can apply the Neyman-Pearson lemma, and using Neyman-Pearson lemma, we will construct the rejection region as this thing: the likelihood of theta 0 divided by likelihood of theta is less than k. This would be the rejection region of the most powerful test, and so let's calculate this thing. So L theta 0 divided by L theta equals, here we have a single observation, so L theta 0 is just putting theta 0 here, and theta 0 is 2. So 2 times y, and the theta a is theta equals 1, and which is 1 times y to 0, which is 1. This is 1, and so this is 2y, and rejection region is 2y is less than k. So this is our rejection region, and actually this rejection region is this thing: y is less than k. And so and we know that significance level is alpha, so the probability of rejecting null y is less than k. Probability is of y is less than k, given the null situation the density of y is 2y, and we want to calculate this probability from 0 to k dy. So this is y squared from 0 to k, and this is k squared, and this one is the alpha, which is 0.05, and so our k is square root of 0.05, and this is about 0.2236, and so our rejection region is y is less than 0.2236. So this is our test and decision rule. Okay. Let's move on to example 10.23. Suppose that y1 to yn consists of random sample from a normal distribution with unknown mean mu and known variance sigma square. We wish to test h0 equals mu 0 against h alternative if mu is greater than mu 0 for a specified constant mu 0. Find the uniformly most powerful test with significance level alpha. And here this hypothesis is simple hypothesis because we have known sigma 0, known sigma square, and so we can apply the Neyman-Pearson lemma to find the uniformly most powerful test. So we now need to calculate L theta 0 and also L theta. And here the L theta 0 is L mu 0, and here the normal probability is 1 over square root of 2 pi sigma square e to the minus 2 sigma square yi minus mu square. So L mu 0, this is 2 pi n over 2 and sigma to nth and e to the minus 1 over 2 sigma square sum of I equals 1 to n yi minus mu squared. Okay, and mu 0. Okay, and what about L mu? And actually everything is same, but the mu 0 part is mu. Okay, it's very similar. Then let's calculate L mu 0 divided by L mu, and this is many parts are cancelled out, and e to the minus 1 over 2 sigma square, and this part is sum of yi minus mu 0 squared minus sum of yi minus mu squared. Okay, this is and the rejection region is this is less than k, arbitrary number k, and actually we can take log, and the equation is still hold. So if we take log, then minus 1 over 2 sigma square of this thing is still less than k for the arbitrary k, and also these two k's are not the same k, but what I want to say is that this is arbitrary constant k. Maybe we can specify this is k dash, and and if we cancel this thing, then we can change the sign with k 2 dash of this thing, and this part is sum of yi square minus 2 sum of yi mu 0 plus some constant 1 and minus sum of yi square plus 2 sum of yi mu and minus some constant 2. Okay, and this one cancelled, and 2 mu minus mu 0 sum of yi is greater than k, actually k 3 dash, because this one is constant, this one is constant, this we can move these constants to this side, and so but from here, actually, this relationship is the important thing, and actually this one is also constant greater than 0, because in alternative hypothesis mu is greater than mu 0, so this part is greater than 0. So what you can check is that sum of yi is greater than k first, or we can say that y bar is greater than k. So this is our rejection region. So our rejection region is y bar is greater than k. And to calculate the alpha level, to calculate k, what we usually do is to calculate the probability. Probability of y bar is greater than k under the null, mu equals mu 0. And this probability is y bar minus mu 0 divided by sigma over square root of n is greater than k minus mu 0 divided by sigma over square root of n, and this is 0. No, this is alpha, alpha level. And here actually this quantity we can calculate this. This is z alpha, and this one follows normal distribution, and so we can construct rejection region with significance level alpha from here. So the rejection region would be if from this expression y bar is greater than mu 0. This part is z alpha, so mu 0 plus z alpha times sigma over square root of n. So this would be the rejection region with significance level alpha. Okay, and actually this rejection region is same as the one that we derived from section 10.3. So so from here, what we know is that the one that we derived from the section 10.3 was actually the most powerful test, uniformly most powerful test. So that's the good test to use when you are doing the hypothesis test. Yeah, that's it. Homework for chapter 10.10 are these.